thank you everybody for your patience. We will start now with the next session. This session is from Klaus Graf, the Associate Professor from the Department of Health Science and Technology in Aalborg University in Denmark. And it's our absolute pleasure to have him with us today to talk about his research experiences with the MUSE system. Just so as you know that this session will be recorded and there is a possibility to ask questions via Slido. So there's information on the bottom of each slide on how to log in and log your questions. So Klaus, I'll hand over to you.
Thank you very much, Jennifer, and thank you for allowing me to share our research experiences with the MUSE system. So my background is in biomedical engineering, and I've been administrator of the research MUSE database that we have here at Aalborg University for 12 years now. So let me first start by drawing up the landscape of the landscape of MUSE systems that we have in Denmark. So Denmark is divided into 5 regions, and each region feeds ECG data into its MUSE system. Some regions, like the northern part where I'm located, have both a research MUSE and a clinical MUSE at the university. And our capital region of Copenhagen also has 2 MUSE systems. Next. I mentioned the different MUSE systems in Denmark because I want to emphasize that it's possible to share data between MUSE systems, and this is something that we use for our research. In other words, you can export data from one MUSE system and import that data into another MUSE system. For example, we thought it would be very useful to have access to all ECGs recorded from patients who had an ECG taken as part of their visit to the general practitioner. And in Denmark, we have the highest number of general practitioners in Copenhagen, so we transferred all the ECGs taken between 2001 to 2015 from Copenhagen to our research MUSE in Aalborg. Next, please. So here's a map of the data that we transferred. All 600 general practitioners in Copenhagen, including the 400 medical practitioners, they refer their patients to 8 labs in Copenhagen. And then all of the ECGs are collected in a centralized lab, also located in Copenhagen. So over the period of 15 years, 950,000 ECGs were collected from about 480,000 patients. We were also so fortunate that the labs gave us access to blood work, so we have both the ECG and blood from about 1/3 of the population of Copenhagen. Next, please. Now, when you collect this type of data, there's one problem. When you collect data over many years, not only will you have data from many different ECG machines, but each machine will use different algorithms to analyze the ECG. Also, those algorithms change over time, so that each machine will use a new version of an algorithm as the software is updated. This means that in MUSE, the digital ECG parameters that we can extract, they're not standardized. And in our publications, that can create a problem. So anytime we collect our research ECGs, we need to make sure that they're reanalyzed with the same algorithm. And this is one of the very important features that we use in MUSE when we import data from one MUSE to another MUSE, or from one site in MUSE to a different site in the same MUSE. Next, please. So in our case, when we imported the 950,000 ECGs to MUSE, we used the reanalysis option that you can set in the system. This way, we make sure that all ECGs that end up in one site in the ECG database are analyzed with the same and the most recent version of the 12SL. Next, please. So you can see here a before and an after picture, a before picture of the ECGs that we imported and an after picture. So in the left column, in the red rectangle, is the version that was used to analyze the original ECGs by the ECG machines. And you can see that they're not all the same. And in the right-hand column, inside the rectangle, you can see that the version that we used upon reanalysis is all the same. So why do we do this? Why do we do this when we perform research? Next, please, Jennifer. Well, we do this because when we publish our results, it's very important for us to write in our methods section that all ECGs are analyzed with the same version. And why is this important? Well, this is important because, of course, we want to report findings that are caused by disease and not findings that are caused potentially by differences in different algorithms. Yes. Next, please. Another feature in MUSE that we also use every day is the ability to allow researchers from many different institutions to log into the MUSE, and then to allow and to use the specific sites where their data is located. So we can give each researcher a specific profile that allows them to interact with their data in a specific way. For example, it may be that we can allow some researchers to export data and other researchers will then not have that option. Next, please. We can also allow each researcher to build a personalized statement library if that is a requirement for a project. And here's an example from one of our projects where statements are related to the long QT syndrome and Brugada syndromes. And this is very useful when we wish to tag ECGs so that we can find them later. For example, if we want to analyze a particular subgroup of our data, we have a meaningful tag for the groups. Next, please. So I also want to show you a number of different ways that we use to extract data from MUSE. So very often we're interested in standard ECG measurements, such as the heart rate, the PR interval, the QT interval, and so on. And these parameters we find rather easy to extract from the SQL tables in the MUSE system. And I show you here an example of one SQL table that has those standard ECG measurements. With a few clicks, this table can be exported to Excel or comma-separated files. And it's then easy to work with in most statistical programs we find. But of course, sometimes we are interested in not just the standard ECG parameters, and there are more than just the standard ECG measurements available in the SQL tables. Next, please. So if you look at this template ECG, you can see that amplitude and interval measurements from all the deflections in the ECG are available. So not only that, they're available individually in each of the 12 leads of the ECG, and we're also able to export those intervals and measurements individually on a lead-specific basis. Next, please. So now, let me give you an overview of the framework that we have for the Copenhagen General Practitioners ECG data that I mentioned in the beginning of my talk. So you can see here that we have MUSE users from many different research institutions who can log into the MUSE. In MUSE, they have access to the 950,000 ECGs and the ECG parameters that we can measure from those ECGs. But we've also been able to link the ECG measurements to the Danish health registries that has detailed information about the medicine and diagnosis and causes of death in these patients. And this is a very strong setup because it allows us to study the associations between ECG measurements and the development of disease. Next, please. So for example, using the ECG database and the Danish health registries, we've examined the association between different ECG measurements and new onset atrial fibrillation. So here you can see that we've looked at heart rate, the PR interval, the QT interval, the duration of the P wave, and also the presence of interatrial block, IAB. And all of those measurements come directly from the 12SL measurements in MUSE. Next, please. So for example, in our study of interatrial block, we use the definition of block, which is a characteristic of the P wave where the duration is prolonged or the morphology is biphasic in inferior leads, leads 2, 3, or AVF. This information can then be found in the Excel files that were exported from the SQL tables, and we can then do our association analysis with different outcomes, as you can see on the right-hand side. Next, please. So I also want to show you how we've been able to use existing ECG parameters to reassess some of the diagnostic ECG criteria that we use every day. And the example that I will show you is the criteria for left ventricular hypertrophy, but we're also doing the same thing for left atrial enlargement. Next, please. So here we used our Excel files with the 12SL ECG measurements to quantify 6 different ECG criteria for left ventricular hypertrophy, as you can see here in the table. We then compared those findings to CT images yes, go back, thank you. CT images of the left ventricle in nearly 5,000 patients, and we're actually surprised to find that there was only a 4% overlap between ECG criteria of left ventricular hypertrophy and organ damage by CT. In other words, the ECG criteria for left ventricular hypertrophy that we use every day in the clinic may not actually reflect the degree of organ damage. So you can see we can also use MUSE to reassess, establish criteria for disease, and then hopefully we can find ways to improve them in the future. Next, please. Another useful feature for research in MUSE is the search function. So let's say you want to measure the QT interval, and we want to exclude certain ECGs from our analysis. For example, we want to exclude ECGs with bundle branch block and wide QRS because they can disturb our interpretation of the QT intervals. So we can then do database search to find all those ECGs that we wish to exclude from our analysis. Next, please. So here, for example, I wish to exclude ECGs with the diagnosis of left bundle branch block. In Danish, as you can see there in the highlight, that is abbreviated VG. Next, please. So we also require that the excluded ECGs will have a QRS duration greater than or equal to 120 milliseconds. Next, please. And we then do our search. And in this example here, we found a total record. We found 8,865 records from 4,700 patients. Now we have our patients that we wish to exclude from our study. And I apologize that the statements here are in Danish, but I can tell you that they all have the same diagnosis, and that is reflecting the search, namely left bundle branch block and wide QRS. Next, please. And as you can see here, these searches translate directly into the methods sections in our research papers, where we describe what patient groups we have excluded. Here, for example, we've excluded patients with bundle branch block and wide QRS, what I just showed you. Next, please. It's also possible, as many of you may know, to manually measure intervals and amplitudes in MUSE. And this could be done in a blinded manner to the 12SL measurements in different ways. Next, please. This is important because we can then use the manual measurements to quantify the agreement between the automatic measurements from 12SL and our manual measurements. And many times in the review process of our research, we are actually asked to do this type of comparison on a random sample, small sample of the data. So we find this also a very useful feature, and it directly translates into our research papers. Next, please. Sometimes we also use the 12SL measurements from MUSE together with the Danish health registries to assess the risk of cardiovascular death. Here I've shown two studies that we're doing, one with the QT interval and cardiovascular death, and another study with the morphology of the T-wave and cardiovascular death. Next, please. Now we can use our ECG measurements in combination with conventional risk models for cardiovascular death. So here we can see that for a 55-year-old woman with no apparent disease, her risk of cardiovascular death within 1 to 10 years is not affected very much by the different levels of QT interval, only about 1 to 2% when the QT interval fluctuates. Next, please. Yes. In contrast, if you have a 65-year-old man with several, no, go back, please. Yes. In contrast, if you take a 65-year-old man with several comorbidities, his risk of cardiovascular death depends very much on the magnitude of the QT interval on the ECG, because you can see his risk changes 20 to 30% when the QT interval fluctuates. So this is just one way to use ECG measurements from the MUSE to improve conventional risk models for cardiovascular death. Next, please. Yes. So now we've come to what I think is one of the most powerful research features in MUSE, and that is the ability to export the ECG in different formats, such as PDF format or XML format. Next, please. Many times we will export PDF versions of the ECGs, and then we will circulate them for review. Many times we will do measurements of specific intervals on these PDFs, and we will then use those measurements to compare with the automatic 12SL measurements. Next, please. But I think the most important format that we use in our research is the XML format that we can export from MUSE, because here we have everything in one single file. We have the annotations of fiducial points, so we can know where all the intervals are measured on the ECG waveforms. We have the ECG measurements in the measurement matrix. I've highlighted some of them here in the red rectangle. But more importantly, we also have access to the raw ECG waveforms because they're included in the export of the XML files. Next, please. And I say that the XML format is very useful for research because they allow us to use these XML files in custom written software that we develop ourselves. So here's an example of a graphical user interface that we've built in MATLAB, where we import the XML files exported from MUSE, and then we show the ECGs using the 12SL fiducial points from MUSE. So we don't have to write our own algorithms. We can simply use the fiducial points that have been validated already. Next, please. So with the XML files, we can do also advanced signal processing. For example, here we've transformed the ECG into a vector cardiogram, and you may ask, well, why on earth would we want to do that? Next, please. But we do that because we can then derive novel ECG measurements from the XML files. Sometimes we will see novel ECG parameters in research, and we may want to derive them ourselves. And this is an example of one of those more recent ECG markers of heart failure, the so-called QRS area or the QRST area that we have derived directly from the vector cardiogram that we obtain from the MUSE XML files. Next, please. Because in talking about novel use of the ECG, I also want to give you an example of how we use the MUSE XML files in deep learning with neural networks. So in one example, we have compressed the ECG into a simplified description of the ECG by a few reduced set of features, for example, 30 features. And if those 30 features capture all the information in the ECG, then they can also be used to reconstruct the original ECG again with little or no loss. And hopefully, we can then find meaning for these features. We can see, for example, what happens if we change one of the features, and here apparently feature number 16 controls the amplitude of some segments, and feature number 10 then controls other features. So how do we then plan to use this type of research, this type of advanced signal processing? Next, please. So in the ideal situation, I talked about extracting 30 or describing the ECG with 30 features. So in the ideal situation, we could have a, let's say, 30-dimensional space of features, and I've shown here a very colorful plot of only two-dimensional representation of this feature space. And in this space, similar diagnoses from the Danish health registries might cluster together. So if we record a new ECG and we ask ourselves a question, where in this cluster will the new ECG be placed? And what are the diagnoses closest to this new ECG? Then we can go on to find the most probable phenotype of this new ECG, but we can do even more than that. We can then ask the neural network, to indicate on the ECG why a specific diagnosis is likely. And this can be done with the so-called attention mapping technique. And here you can see that it has indicated a 99% chance of right atrial hypertrophy, and it has also indicated in red the upsloping part of the P wave, which then would be indicative of the right atrium being enlarged. So now, not only will you have information about a diagnosis, but we'll also be able to open the black box that we usually talk about when we talk about neural networks, and then we can understand why a particular diagnosis was suggested, but also what is the certainty associated with this diagnosis. Next, please. Yes. So this will be my final slide here. So you can see in a summarized view here how we might be able to use MUSE in the neural network framework. So we suggest to use MUSE to pave the way to new knowledge and potentially better treatment. So how can we do this? Let's say you go to your doctor, he records an ECG and uses then a neural network to get the most likely diagnosis. A phenotype is suggested. With this diagnosis in hand, we then go on to look up how people with this diagnosis historically have been treated and what their chances were of survival. We feed this information back to the doctor so he can make an informed decision about the treatment of his patient. And hopefully this new knowledge will then lead to better treatment of the patients. Yes? Last slide, please. Yes? So thank you very much. This concludes my presentation. Thank you very much.